So here we are going to discuss some basic aspects of solid state. Okay. So we all know that matter exists in different forms, right? Solid matter exists in different forms. Okay, what are they? We have solids, we have liquids, we have gases. These three are the main states of matter. Okay, apart from this we have other states like plasma state is there, and Bose-Einstein condensate also there. So there are many states, but these three are the main states of matter. Okay, solids, liquids, and gases. And we all know that solids is one in which the intermolecular attraction, okay, is very, very large. So intermolecular force, I'm using the term intermolecular, but in solid the particles need not be molecule, okay, it can even be atoms, it can even be ions, right? So just for here I'm using the molecular term as a general term. Okay, so intermolecular forces, okay, is very high. In case of solid, intermolecular forces are specifically attractive force is very high. Okay, that's why once atoms or molecules or ions they combine and form solid, then they get locked in their positions. Okay, each and every atom or each and every molecule get locked in their position, they cannot move. Some lattice vibration may be there, small vibration may be there, but on average all the atoms or all the molecules or all the ions are present, okay, in same position. The position never change. Okay, whereas the other two states, liquids and gases, okay, in these two states the particles, I'm using a common term here, particle may be atom or molecule or ions. Okay, so the particles in liquids and gases, right, they can move freely because intermolecular attraction is very less compared to this. Okay, so and we combinedly call these two states, liquids and gases, in general as fluids. Liquids and gases are generally called as fluids. In fluids, intermolecular force of attraction, intermolecular force is comparatively less. If you compare to this, it is less. Okay, is less. Right, since intermolecular force are less, here the atoms or molecules can move freely. Okay, and you know very well, among these two, the intermolecular force of attraction is very, very weak in the case of gases. So in gaseous state, molecules can move randomly here and there. Okay, it is because of less attractive forces. Okay, yeah. In this chapter we are going to focus mainly on solids, structure of the solid, right, and what are the informations available about solid structure. Then we are going to discuss how to identify the structure of solid using different techniques that is available. Okay, then we are going to see some of the important aspects of solid state, right? But in solid state topic, I am going to discuss only the basic ideas. I am not going to discuss many in-depth concepts over this chapter. Okay, right. So this is the introductory. This is the information about solids. Okay, now here I am going to use a common term that is particles. Particle or particles, which means in the case of solid, a solid may be formed, okay, just by the combination of atoms. A solid may be formed by the combination of molecules. Molecules aggregate, okay, many molecules aggregate together and form solid, okay. And solids may also be formed by the combination of ions, okay. And these atoms or molecules or ions which form a crystal or a solid are generally called as constituent particles. Often we say that they are constituent particles. Constituent particles of a solid may be atoms or molecules or ions, okay. So hereafter I am going to use the term constituent particle simply. I am not going to use the term atom, molecule, ions here, okay. If I say constituent particle, it means that the atoms or molecules or ions that is present in the crystal, okay, right? Yes. Solids are classified mainly into two. How solids are classified, okay. This is how solids are classified. Solids are mainly classified into two. Number one, amorphous solids. Amorphous solids, okay. In amorphous solid, you know very well, the atoms or the constituent particles are arranged in a random manner, okay. In amorphous solid, constituent particle, let me write shortly CP. CP means constituent particles. In amorphous solid, constituent particles, right, are arranged in a random manner. In random, okay. There is no definite arrangement, okay. They are arranged, they aggregate together in a random manner and exist as a solid, okay. Amorphous solids, right? Example, there are plenty of examples are available, but I like to give this example: silicon dioxide glass, okay. Silicon dioxide glass is an example for amorphous solid. Apart from this, you have rubbers, plastics, many examples are there, okay. So this is the information about amorphous solid, okay. Introduction, okay. Introduction about amorphous solid. Amorphous solid is a solid where constituent particles are arranged in a random manner, okay. Constituent particles are arranged in random manner, okay. Example, SiO2, silicon dioxide glass. Then another classification, another important solid, right, is the crystalline solid. You might have heard about this in your 11th or 12th. Okay. This is the second category called crystalline solids. In crystalline solids, constituent particles are arranged, okay, in a definite order, okay, in 3 dimension. Observe carefully, right? In crystalline solid, constituent particles are arranged in a definite order in 3 dimension, okay. So this is the important fact about the crystals. In a crystals, constituent particles are arranged in a definite order, okay. And plenty of examples are there, okay, but I'll give one example here. SiO2 crystal, SiO2 crystals, we can say quartz crystals, QUARTZ. Quartz crystals, right, are actually silicon dioxide crystal, solid containing crystal silicon dioxide, but it is arranged in a definite order. Here see, here also silicon dioxide, but here the arrangement is not in a definite order. The arrangement is completely random. So silicon dioxide glass is an example for amorphous solid. Silicon dioxide crystals, also called quartz, okay, that is an example for crystalline solid. Apart from this, you know very well, in the periodic table, most of the elements, right, apart from liquid and gaseous element, most of the elements, solid elements, okay, they have a definite crystal structure. They are all crystals, okay. All solid metals, let me write here, all solid metals, especially all solid metals are crystals. I am using the word solid, okay, because you know very well some metals exist in the liquid state also. So all solid metals are crystals. Copper, silver, gold, right, zinc, cadmium, whatever metal you take, they belong to some crystals. Okay, we are going to discuss about crystal structure, but right now I am just introducing you what is a crystal. In crystal, constituent particles are arranged in a definite order in 3 dimension. Okay, yes. Right, listen, see, constituent particles, if they arranged in a random manner, we can call that solid as a amorphous solid. If the constituent particles arranged in a definite order, then we can call that solid as a crystal. Okay, and one more information about crystals. Actually, many informations are there, okay, by which you can differentiate an amorphous solid and crystalline solid, right? Let me give that in different points like this. Amorphous solids. These are all certain characteristic features of amorphous solid and crystalline solid. Crystalline solid. Okay, what are the features? Right here, number one. As I said before, in amorphous solid, the arrangement is constituent particles are arranged in a random manner. Okay, I said random manner. Whereas in crystalline solid, constituent particles are arranged in a definite order. There is a definite order, right? Definite order of arrangement exists. Definite order. Okay. Then next important point is that in the case of amorphous solid, if you measure the refractive index, okay, of the solid in different directions. Suppose, see, I'll take some solid. The atoms are arranged in a random manner. Okay, we measure refractive index in this direction. Let me take this N1, where N is the usual symbol for refractive index, and I'll measure the refractive index in this direction. I'll measure the refractive index in this direction. Okay, in whatever direction you take, on average, the refractive index values are equal in the case of amorphous solids. Okay. Yeah, in the case of amorphous solids, right, the refractive index values on average, okay, this value and this value, they are all equal. Okay, since they have same refractive index everywhere in all directions. Not only refractive index, you can measure other properties like thermal, electrical conductivity. Okay, you can measure other properties also. In amorphous solids, whatever direction you measure the property, you will get same result in all direction. That means amorphous solids are isotropic in nature. Isotropic in nature. Note down, it's very, very important. Right? In whatever direction you measure the refractive index for a amorphous solid, you will get same result. Right? So here N1, N2, N3, they are all equal. Okay, because since the solid is random, right, the interaction between the radiation and the particle on average it is same in all the directions. Okay, so keep this point in mind. Amorphous solids are isotropic in nature. Whereas if you come to crystals, in crystal, suppose I'll take a crystal formed by two different atoms, say A and B, A, B, A, B, A, B, like that. Near to A will be having B. Like that, a crystal is formed, okay, in this order. AB, AB. This is an assumption. I'm just showing you a two-dimensional layer. Actually crystals are three-dimensional. Okay, real crystals are three-dimensional. I am showing you only the two-dimensional layer. Right? Now observe this carefully. Suppose if I pass a radiation in this direction, and if I measure the refractive index in this direction, see this radiation, see the right hand side and the left hand side. Suppose see this side of the radiation and the other side of the radiation. Right? Here I have A, I here have B. A, B, A, B, A, B. Or in the direction of the radiation, okay, you take this arrangement alone. I have A, B, A, B, A, B, A, B, A, B, A, B, right? Okay, so this radiation interact with the crystal in one type. Now I'll take another radiation that passes in this direction. Now see, for this radiation, see these particles are just B, 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 and the other direction we have only A, 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 A. See the difference. In this direction, the arrangement of particles is A, B, A, B, A, B, A, B, like that. Whereas in this direction, see, one side I have only B atoms and the B particles, and the other side I have only A particles. Therefore, the interaction faced by this radiation with the atoms or particles and the interaction faced by this radiation with the particles are not same. So, in this case, the refractive index measured in one direction and the refractive index measured in the other direction, they are not equal. They are not equal because in crystals, okay, the order in one direction is a definite order, and the order in the other direction of the same crystal, okay, it is entirely different. You have definite order, but the arrangement is different. Therefore, the property like refractive index or electrical conductivity, okay, or any other property, if you measure, you will get different results in different directions. Okay, that is the reason why crystalline solids are called as anisotropic crystals or anisotropic. Aniso, A-N-I-S-O, anisotropic in nature. Okay, it's very important. Crystals are anisotropic, whereas amorphous solids are isotropic in nature. Right? And this is another important characteristic property of solids, amorphous solids. If you take amorphous solid, they have melting point, or will provide the melting point of amorphous solid in a range. Okay, they have a range of melting point. Range of melting point. I'll write shortly MPT, meaning melting point. Suppose if we take some glass, usually glasses are amorphous. Right? If I give a glass piece, if I ask you to find the melting point, we say generally that it melts between 60 to 65 degrees Celsius. We cannot give the sharp melting point, we can give only the range. Okay, the glass melts between 60 to 65 degrees Celsius. It can melt at 61 or 60.5 or 64.5, whatever it is. We can provide only the range in the case of amorphous solids. Whereas crystalline solids, they have sharp melting point. Crystalline solids have sharp melting point. Okay, each and every crystalline solid, they have sharp melting point, right? Say for example, ice is a crystal, right? At what temperature it will melt? Exactly at the 0 degree Celsius, right? And it also pressure dependent. Don't worry about that. If the atmospheric pressure is 1 atmosphere, then we can say that ice melts at 0 degree Celsius. See, 0 is a specific value, whereas here for glass I am giving you range. See that? Okay, so for amorphous solid we provide only range of melting point, whereas in the case of crystalline solid we will provide sharp melting point, because crystals melts at sharp melting point. Okay, take down. Okay, listen. So let me just give you the detail again. See, in crystals we classify crystals into different types. Okay, these are the different types of crystals we have. Number 1, ionic crystals. Number 2, covalent crystals. Number 3, molecular crystals. Number 4, metallic crystals. Number 5, group 8 crystals, or according to modern period table it is group number 18. Okay, group number 18 crystals. We also call them as frozen noble metals. Okay, now in ionic crystals, constituent particles are ions. Let me write here CPs. Constituent particles are ions, and these ions are held together by means of strong electrostatic force. Because of the strong electrostatic force, right, ionic crystals generally have high melting point. Okay, then these are the examples for ionic crystals. These are all very common example you may be knowing. Then in covalent crystals, right, in covalent crystals, these constituent particles are usually non-metal atoms, non-metallic elements. Non-metallic atoms are elements. Non-metallic atoms, okay, are generally are general constituent particles of covalent crystals. In covalent crystals, these non-metallic atoms are held together by means of covalent forces, covalent bonds. Okay, there are plenty of examples available. Okay, silicon solid, right, solid silicon, right, solid germanium, right, where between atom we have covalent bonds, right, and these have covalent bonds, therefore they have somewhat high, somewhat moderate melting point. Okay, they have sharp melting point. All are crystals, they have sharp melting point, but compared to ionic crystals the melting point is less. Okay, compared to IC means ionic crystals, compared to ionic crystals, okay, melting point of covalent crystals CC is less. Okay, then third category, molecular crystals. In molecular crystals, see, constituent particles are molecules, right? Constituent particles are distinct molecules. Okay, and these molecules, they are held together by means of van der Waals forces. They are held together by means of van der Waals force. Okay, or hydrogen bonding interactions. Van der Waals force or hydrogen bonding interaction. Because of these interactions, okay, the constituent particles, right, they held together and form the solid. For example, in the case of ice, water molecules are held together by means of hydrogen bonding, right? And we have other solids like iodine. In iodine crystals, iodine molecules are held together by weak van der Waals forces. They are all examples. These are all examples for molecular crystal. Actually, we have plenty of examples. I am giving you only few here. Okay, right? So examples are H2O solid, that is ice, iodine solid, iodine crystals, right? Like that we have plenty of examples. Okay, and what about their melting point? Melting point is low compared to covalent crystals. These molecular crystals have low melting point. Okay, then the next one is about metallic crystals. In metallic crystals, the constituent particles, let me write here Cp. Constituent particles are metallic atoms. Constituent particles are metallic atoms, or I can say in another way, metallic ions. Metallic ions form the lattice, and the free electrons, they move around the crystal, and between the free electrons and the metallic ions which form the crystal lattice, between them there is a strong attraction. Okay, so here what type of attraction exists? Yes, here the attraction is somewhat different. Listen, when many metal atoms, observe carefully, when many metal atoms come closer and form molecular solid, each atom will lose one or more electron and form ions. I repeat, when many metallic atoms come closer and form a solid, what they will do? Each atom release one or more electrons. When they release electron, the atom become ion, and the released electrons, called free electrons, they move freely throughout the crystal, and between the metal cations and the free electrons there is a strong attraction, and this attraction is very strong. Okay, that's the reason why some metals have melting point even greater than ionic crystals. Okay, it's very important, right? Then examples, right, in metallic crystals, right, the metal ions and electrons are held together by means of some electrostatic force. Again, it is also electrostatic force. But what is the difference between ionic crystal and here? In ionic crystal, one cation may be attracted by 4 negative ion or 6, okay, that is surrounded negative ions. Okay, usually it is less than 10. Whereas in the case of metallic crystals, each metal cation is attracted by infinite number of free electrons that is available in the crystal, or huge number of free electrons that is available in the crystal. Okay, so that's the reason why this attraction is extremely strong. Okay, that's the reason why these metallic crystals have melting point sometimes even greater than ionic crystals. Okay, keep that in mind. Then in metallic crystal we have plenty of examples: copper, silver, gold, right, platinum. There are plenty of examples. Okay, and they have quite high melting point. Melting point is high, right? And we are going to discuss this frozen noble metal, right, at the end of this chapter. Okay, so right now keep this in mind. Actually, noble group 18 elements are gases, but if you condense them, first it form liquid, then if you cool to very low temperature, you will get frozen solids, and these solids are called frozen noble metals. Okay, they form a different class of crystals. Okay, we are going to discuss that in a separate heading, or in a separately we are going to discuss at the end of this chapter. Okay, right. So these are the different types of crystals we have, right? See, in the case of metallic crystals, listen, let me show you in the next page. Observe this carefully. In the case of metallic crystals, right, what happens is that, see, suppose I'll take silver atoms. I have silver atoms, many silver atoms. Okay, many number of silver atoms. When they form solid, suppose what will happen if we ask each silver atom, when they form solid, each silver atom lose one electron, it release one electron and become metal cation. And what will happen? These metal cation form the crystal lattice. See, Ag plus, all the lattice points are occupied by silver cation, Ag plus ion. We call them as metallic cations. Each metal atom lose one electron. Listen, in the case of silver, each silver atom will lose electron. But if you go to some other elements, say zinc, if you take zinc, each zinc will lose 2 electrons. So the number of electrons that a metal can lose, it depends on the valency of the metal. Okay, so like that, many silver ions, though they have same charge, okay, they form the lattice. How the lattice exists? Because the free electrons, okay, you have lot of, let me put these dots. These dots are nothing but free electrons. You have huge number of free electrons. Okay, and these free electrons move randomly throughout the crystal, like gas present in a container. It can move freely. And listen, there is an attraction between each cation with the free electrons here and here. Okay, throughout the crystal there are many free electrons available, so they keep on attract. And this attraction is not just 1:1. Each cation is attracted by huge number of electrons, and each electron is attracted by huge number of metal cations. Okay, so I can say simply that it is 1:infinite attraction. One metal cation.
Hello, sir.
So when many metal atom, here I took silver as an example. You take many silver atoms. If the silver atoms combine and form solid, okay, metallic crystal, what actually happens is that each atom lose, in the case of silver, valency of silver is 1. So each silver atom lose 1 electron and become silver ion. Okay, so you will get many silver ions, and these silver ions, okay, they form the lattice. Right? You may ask a question, so how cations, right, in adjacent position, how they can exist? They have same charge, no? So repulsion dominate, right? But this is possible because the free electrons that is available, right, they move freely throughout the crystal. Each cation is attracted by many number of free electrons present in the gas, and each electron in the gas is attracted by many silver ions. This attraction is very strong compared to the adjacent silver repulsion. Okay, so that's the reason why the metallic crystals, in general, metallic crystals have high melting point. Okay, right. What is called space lattice. What is meant by space lattice? Also called crystal lattice. Take down. Space lattice, also called crystal. I'll repeat. So space lattice or crystal lattice. What is meant by this? I have told you crystals are formed by either atoms or molecules or ions. We call them generally as constituent particles. Okay, here I have written in a simple short form as CPS, meaning constituent particles. Remember, constituent particles may be atoms or molecules or ions. Right? Listen, if you put dots for each constituent particles, right, you will get an arrangement. I have shown. See here, I am showing you an arrangement in the plane of the paper. So it is 2-dimensional. Right? Then connect the neighboring constituent particle with straight lines. Okay, you will get a kind of pattern. Now, what I am trying to say, similarly, you take another layer over this, another layer over that, another layer over that. Similarly, you keep layers below this. Okay, so this is a layer. Below this, you keep another layer, another layer, and connect the upper layers with the downward layers, adjacent layers. Okay, you just connect the adjacent layers using straight line. If you connect it in this form, we will get a big building block. Okay, that building block is what we call as crystal lattice or space lattice. Okay,